Hello everyone. We are going to continue with our discussion of problems, and in this lecture we are going to consider a slightly different kind of problem. So instead of straight beams which we have been considering till now, we are going to consider this kind of a curved beam. But please note that this is a curved beam under the restriction that it is quite thin. What I mean by thin is that if you consider this dimension, uh, if you consider this dimension, this is the thickness. That thickness, sometimes that is also referred to as the depth of the beam. If what we have here is, uh, suppose this is the center of our circle. So this is a curved beam in the form of a semicircle. So what I'm saying is that suppose our the radius of our circle is capital R, then this can be considered to be a thin curved beam provided uh, R is greater than twice the depth. Okay, so this is our depth. So R is greater, if R is greater than uh, twice the depth, what we say is that our beam is thin. Okay, the question here is, what is the deflection? So the nature of the question is quite the same as what we have been dealing with now until now. So what is the deflection at the point of application of this point P, or the of this point force P? Okay, so deflection, and we are interested in both the vertical and horizontal deflection. At the point of application of the force P. So first, considering the vertical deflection, this is a straightforward application of the Castigliano's theorem on deflection. However, for the horizontal deflection, you note that we do not really have a force at this point which is directed along the horizontal direction. So for that horizontal deflection, we have to consider a fictitious force, but we'll come to that later. First of all, the straightforward case of the vertical deflection, and we'll see what special measure we have to take uh, uh, considering that this beam is indeed in the form of a semicircle. Okay, so the procedure is quite the same actually. In fact, nothing changes. So for the vertical deflection, what we do as before is to take a cut section. Okay, so suppose we take a cut section here. Now, if you consider uh, the free body diagram of the section of the beam which is to the right of this cut section, so it is going to look like this. A slightly rough diagram here. It's going to look like this, and you understand that because over this part there is no externally applied load, so even if you consider this kind of a moment and shear force, both of those values are going to be 0. Okay, so had there been some load at this end or somewhere else on this portion of the beam, then certainly we could have non-zero values of this bending moment and shear force, but we do not have those things. So it is as if the part of this beam from this point up to this point, it is kind of inert from the point of view of the load. Okay, it does not mean that it does not deflect. Of course it deflects. You understand that when this thing is acting downward on it, the whole beam will move slightly downward. As a result, all the material points which constitute this portion of the beam, they will also deflect downward and rightward. But in terms of the internal resistances that show up, they are inert. Okay, so what do we do? So we consider a cut section here, so that instead of this kind of a free body diagram, which doesn't really give us much, we instead have this portion of the beam now, okay, as a result of this cut. Now, of course, the externally applied load will be very much appearing here, and the bending moment, sorry about that, the bending moment is here, the shear force is here. And again, I urge all of you to please make a note of why the default positive sense of this moment and shear force are directed in the way that I have drawn here. This has to do with the choice of our coordinate system, and the coordinate system that we are indeed choosing is this r theta system. So this is our r, and this is our theta, okay, measured from this horizontal. So you think for a moment about the positivity of this, or the positivity convention of this shear force and the positivity convention of this bending moment, and convince yourself that so convince yourself that this is indeed the correct thing. So let me also check this. So r, if you consider the theta to have rotated all the way here, this r is going to come here, and this is going to be directed in this sense. So that is very much the correct sense of the shear force. Regarding the m, this m basically comes about as a result of the sigma theta theta, which will be directed in this fashion. And I think I have to make this reverse. Sorry about that. So you understand that this r is in this sense, and the sigma theta theta is in this sense. So let me just draw that. My sigma theta theta will be in this sense, which means that if I take the moment arm to be r, it is going to curl downward, which means that the sense that I have drawn here for the m, and that has to be changed. Okay. So this is my m. Now, what is the expression for this m? You see, the m here is going to be balanced by the contribution to the moment which is imparted by this force P. The moment for this force P will be calculated about an axis which is passing through this end. And for that, the moment arm, you note, is going to be this portion. This is the moment arm for that. So this distance, that is going to be the moment arm. And what is that? So, so you understand that this particular angle okay, so if this entire thing is theta, let me clarify that diagram. if this entire angle is theta, then this particular thing is theta minus pi by 2, and uh, if, and this radius of course is capital R. So this distance is going to be R times sine theta minus pi by 2. So let me write that down. So force and the moment arm, that is R sine theta minus pi by 2, and the sense of it uh, is opposite to this bending moment M. This M is in the anti-clockwise sense, and the contribution to the moment from this force P will be in the clockwise sense. So uh, this is minus. Now we have to be very careful in incorporating the heavy side or the step function, because as we have just discussed, uh, this portion from theta equal to 0 to pi by 2, that is not going to contribute anything to the moment. So this is our expression for M. So all that we have to do for finding out the vertical deflection, I write d with a subscript v to denote the vertical deflection. That will be equal to integration 0 to pi uh, and even before I write this, it should be a little bit more systematic. So what I'm doing here is d del u del p, and the u, as before, the strain energy, that is very much m square by twice ei. Earlier, for the straight beams, in this portion, I used to write this as dx, and I used to carry out the integration from 0 to capital L, which was the entire length of the beam. Now the entire length of the beam is given by this r times pi. Okay, so the elemental portion of that while traversing in this theta direction will be r d theta, and we are going to carry out the integration from 0 to pi. So overall what we are going to have is this 0 to pi m by ei del m del p r d theta. So the rest of it is just carrying out the integration steps, so I'll not do it here. Instead, I'll just note down the answer here, which is uh, 5 pr cube by 4 ei. Okay. Now, the next thing that we're going to try is the horizontal deflection. Okay. So I'll just copy this figure and go to the next page. Now everything remains the same as before, but now what I want to do is include here a fictitious force. A fictitious force q in the horizontal direction. And now as a result of this, what is my m? So this m is still like this. The contribution to the m due to the p will be exactly the same as before. So this is p times r sine theta minus pi by 2 times heavy side theta minus pi by 2, and again this comes with this minus sign, Now we have to consider the contribution to the moment due to this force Q, this fictitious force Q, which will ultimately set equal to 0, this force Q about an axis which is passing through this end. And this time you note that the moment arm for this force Q is this distance. It is this distance. Okay. So earlier it was that distance for the force P, and here about this end, from this end, the moment arm is this vertical distance, and that vertical distance is so we write Q first, and then this is R. So you please note that this entire distance is R, and this particular distance, okay, so from here what I'm saying is that this distance, this particular distance is going to be R cos theta minus pi by 2. Okay, so it is going to be and again it comes multiplied, or it should be multiplied with this heavy side of theta minus pi by 2. So this entire thing. Okay, and you please note that again the sense of the moment due to this Q is in the clockwise direction about this axis passing through this end, so it should be again with this minus. This entire thing is equal to 0. So just like before, what we have to do is for the horizontal deflection, so DH, the H subscript stands for the horizontal deflection. So it should be del U del Q, but evaluated at Q equal to 0. So this is again as before, we carry out the integration from 0 to pi to cover the entire length of the beam, and just like before we have to be very careful in noting that this entire calculation has to be carried out at Q equal to 0. Maybe I should just write this thing outside. If we actually carry out this the intermediate steps, what we'll finally obtain for the horizontal deflection is this PR cube by twice EI. All right. So those are the answers for the horizontal and the vertical deflection. Now, we can have various other variations on this circular problem, and then if you, for example, you could be asked to find out the reaction forces for a statically indeterminate kind of a beam structure involving such a curved curved orientation or curved nature of the beam in a fashion similar to our earlier problem where we considered a structure where the effect of not only the bending but also the torsion came into play. in a similar fashion, we can have a structure where part of it is just like a curved beam and another part is maybe straight. So we can have various combinations of the things that we have learned as part of different problems. Okay, so it can get very, very interesting. So on that note, I will end this lecture. Thank you very much.